Hey, Emmanuel.
Hey, Professor, how's your weekend?
Good. How's yours?
Pretty good. Actually had a quick question on the homework if you have a second.
Sure. Yeah, what's up?
Um, so on prop for the one with the eyeball,
Yep.
um, when you're doing the thermal circuit without the contact lens,
Mm-hmm.
um, so I'm kind of confused on which radius do you use for R outer because would you just use the same like radius two to calculate the surface area?
Right. Yeah, so in that case, since you don't have the contact lens, then the outside air is basically in direct contact with your cornea. And so the R that you would use in the convection resistance would be R2.
Okay, that's what I thought. And then on the cylinder one with the tube,
Yep.
uh, or where you have the first on part C where you add the chemical spray, it doesn't say anything about the radius increasing. So do you just assume that it's like negligible?
Right. Yeah. So the spray is just a very, very thin layer. So there's no radius increase. So it's just, it's just like you spray paint on the outside of the on the pipe, basically. Mhm.
Okay, I'll keep working through it, but I for some reason I'm getting like not very close to what your answer was. I got one that was like 146 as a temperature and another one that was like 22, but I'll work it out again.
Okay. Yeah, if you're still having trouble with it, I'll be available after the lecture today, so we can I can take a look and help you out with it.
Okay, great. Thank you.
Yeah. Mhm.
Professor, I have a quick question.
Sure. What's up?
So on the exam, will there be like conceptual questions like how you have at the beginning of the homeworks where it's kind of like you just explain your answer?
Yep.
Okay.
Yeah, so the format for the exams, usually what I do is I have 4 short answer questions and 3 problem solving questions.
Okay.
But since the exam is going to be virtual, I'm going to cut 1 question off of those off of each of those. So it'll be 3 short answers and 2 problem solving questions on the exams.
All right. Sounds good.
Mhm.
How's your 3-day weekend, Professor?
It was good. Yeah,
good.
I spent most of my day off just running errands and cooking actually. So my fiance always brings a bunch of fruit back home from work because she has a coworker that lives in a retirement community, and they have, you know, each of the retirees there has like a tree, either like an orange tree or lemon tree or grapefruit tree, that grows too much fruit than they can consume. So he's always giving away fruit. So I turned a bunch of that fruit into just orange juice and grapefruit juice on Monday. So
Nice.
that
Have
was
you
good.
tried to do preserves?
No, I haven't actually. That's a good idea though. Maybe I should check that out. But
Yeah. You would, from what I've known, at least because my mom and grandma from time to time, whenever we grow stuff in the garden, that's what they usually would do.
mhm.
They usually use a pressure cooker to help with the sealing. And there's some recipes I think they use to do like the initial putting the ingredients together.
Mhm.
And the other thing is you would need to get like a jars with it's kind of like a combo type of lid where it's like the screwing part. There's like a, I don't know what's it called, but pretty much like the when you screw the top, there's like a kind of cutout in the middle
Mhm.
where it's just kind of like a hollow-ish, and then there's like a actual lid that rests on top of the the glass jar.
Okay,
So that's the sealer in a
I see.
sense.
I see. Cool. Yeah, I'll definitely look into that. Yeah, maybe we can talk more about it after the lecture. But it is time to start. So good afternoon, everybody. Welcome back from the long weekend. So how's everyone doing today?
Not too
Pretty
bad.
good.
How's the weekend?
Good, good. Yeah, I was just telling Nicholas that I spent my day off producing a lot of fruit juice because we have a lot of fruit that my fiance brings home. Okay, so today's a little bit busy, so I do want to get through a lot today, and so we'll see how much we get through it. But I want to basically finish up our lecture notes here on fins and multidimensional heat conduction. Okay. And so before that, there is one thing I want to, because I graded your homework ones last week. And so there's one thing I saw a lot of you guys do on that homework that I want to address too, okay? And just one more announcement too, that the next homework 2 is due tonight. And so that's due tonight at 11:59 p.m. on Canvas, right? And so I plan to probably grade those on Friday. So then you'll have the grades for that too. And then once that homework's done, I have your next homework prepared. And that's going to be due in 10 days. So that's going to be due on Monday of week 6. Okay. Okay. And so besides that, are there any questions that I can answer on? I know there's a couple people are struggling with the homework right now, particularly problem 3. And I saw some chatter on the Discord about that. Last night. So I can go over that really quickly at the beginning of class today too. Would people like to see a little bit of how to set up problem 3 on the homework?
Yes, please.
Okay. So let me do that. So let me address something from homework 1, and then I'll quickly go over problem 3, and then we'll go back into fins. Okay. And so on homework 1, the problem that I ended up grading was problem 3, which was the thermal circuit one. But I did look at your problem 2s quite a bit. And there was, I did see, a lot of people kind of make this mistake. So let me kind of address that real quick. Okay. So if you remember in problem 2 for homework 1, you had a situation that looked like this, right? And so we had kind of a thin heater here that was kind of sandwiched in between 2 different slabs, okay? And then what the problem says, and I think, I think this is the reason why, because I think the wording in the problem was a little bit confusing. What I said in the problem was the heater was producing heat, right? Right. So in other words, it's producing a heat flux, which I defined in the problem as Q not double prime, okay? And so what the problem asked you was to find the temperature distribution basically from here to here, okay? Right, so on one end you have x equal to 0, and the other end you have x equal to L, okay? And so since this is a heat equation problem, the way that you solve this was to solve the heat equation, right? And so you start out with the differential equation, looks like this, okay? Right? And so that's your heat equation. And so the part where I think a lot of people got confused was what to do with this term right here, okay? And so if you remember, our Q dot term here is our thermal generation term, right? And so, you know, a lot of you guys included that in your solution when you went to solve it, okay? But actually for this problem, in this problem, you're actually going to cancel it out, okay? So because you're not going to have thermal generation. And so the reason you cancel that out is, you know, here, all the thermal generation is being localized to just one location, right? So the only place where heat is being generated is at the heater, okay? Inside the slabs of the material, you know, there's no heat that's being generated. And that's actually where I wanted you guys to solve for the temperature distribution, okay? And so to kind of sum this up, you know, the only time that you should include this Q dot term okay, the only time you should include Q dot is when there's heat that's being generated within the actual solid. Okay? Or I should say the heat is being generated throughout the entire solid. Okay. And so in this case, because, you know, the heat was only being generated at the kind of the very small heater, the way that you actually accounted for this in your solution is to use a heat flux boundary condition. Okay. Okay. And so if you want more details on how that's done, you know, I did post the solutions for homework 1, so you can check out basically how I solved that, okay? But, you know, when you're solving these ones, you really have to kind of read the problem carefully and see, you know, if there's thermal energy being generated throughout the entire solid. And that's the only time where you should include the Q dot, okay? All right, any questions on that? Okay. All right, so then now let's just review problem 3. Okay, and this is in homework 2. Okay. So this is a bit of a long problem. So there's lots of steps involved, but you know each of the different steps are designed to kind of build on top of each other. Okay, and so what the problem states is that you have a pipe that's transporting liquid nitrogen. Okay. Right. And so you have a pipe that basically looks like this. Okay. And so inside you have liquid nitrogen. Okay. And then on the outside of the pipe, you have it being, in this case, heated up by outside air. Okay. Okay. And so the outside air has a temperature T infinity, and it has its convection coefficient H. Okay. Okay. And so the other things I gave you in the problem where the inner radius here, okay, so this is Ri, and this is Ro. Okay. Right. And so for every part in this problem, you know, what I'm asking you to solve for is the temperature on the outer surface of this pipe. Okay. And so basically that's basically just a compute to say if you're a worker here and you touch the outside of the pipe, you know, what temperature are you going to be feeling, right? And so so the way this problem works is that each part of the problem, we're basically adding additional layers onto this pipe because right now it's way too cold to touch. Okay. Right. And so okay, so the other temperature that we do know is the temperature here, okay, at the inner radius, and so we'll call that Ti. Okay, and so you know basically the way to approach this problem is to basically you're going to keep adding on to the thermal circuit. Okay, and so in the base case right here, so this is part B. Okay, in part B, you basically only have 2 resistors, right? And so at the ends, you have Ti, and then you have T infinity, okay? And then this first resistor that we have is the conduction resistance of the metal part of the pipe, okay? So this would be R metal, okay? And then this resistor on the right here, this is the convection resistance of the outside air, okay? And then once you've set up this thermal circuit, you can then compute the heat transfer. So you can do Q is equal to Ti minus T infinity, all divided by the sum of the resistances. Okay. And then, from here, you can solve for the surface temperature. Okay? And so the surface temperature is going to be right here. So the surface temperature is always going to be the temperature right before the convection resistance, because that's the one that you're physically touching on the outside. Okay. Right. And so just like we've done for all our thermal circuit problems, you can use this to solve for TS, because this Q, since we just have a linear circuit here, is going to be equal to TS minus T infinity. Okay. Or the difference in between these two nodal temperatures, okay, divided by the resistance in between them. Okay? And then you can basically use this expression to solve for TS. Right? Okay, so that's part B. In part C, what I'm telling you is that to better insulate this, what you're going to be doing is you're going to be spraying a special chemical on the outside. Okay, and so you can almost think of it as like you're taking a bottle of spray paint and you're kind of spray painting the outside. Right? So it might look like something like this. And so this layer right here, it's very thin. So it's we wouldn't be able to compute a conduction resistance for this just because the thickness is so small. And so in part C of the problem, what I told you is that we can model this as an additional contact resistance. Okay. Okay. Right. And so if we draw the updated thermal circuit, we're going to have one more resistance on top of this. Okay. Where this is Ti, this is T infinity. This is our metal. This is our convection. Okay. And then this new resistance in the middle right here, this is the resistance of the chemical spray. Okay. Question. So can you find the T's using R metal and Ti? Yeah, you can. So it's so you can either use Ti and TS and R metal, or you can use TS and T infinity and R convection. So you can do either one. Yeah. Mm-hmm. Right. Okay, and then once again, we're going to be solving for TS right here. But remember, TS is on the outside of the cylinder, right? And so TS is actually being located right here because you're going to be touching on the outside of the spray. Okay. Okay. And so you're going to be solving for this temperature right here, and the value for our spray I basically gave it to you in the problem. Okay. All right. Does this make sense so far? Okay. All right. And so part D, what you're going to be doing is you're going to be adding another layer of insulation on top. Okay. And so I think this is where people get confused because the contact resistance is still there from the previous part. It's just we're putting something additional on top of that. Okay. And so now we're going to have 4 resistances in total. Okay? And so our thermal circuit is going to look like this. Okay. Okay. And so now we have this additional insulation resistance right here. Okay, so that was provided by the polymer. Okay, and this does have some thickness. So for this insulation resistance, you're going to use our formula for conduction resistance in a cylinder. Okay, right. And then from here, you're going to compute the temperature right here. Right. So remember the surface temperature that you're computing is always the one right before our convection. Okay, but you're going to set up the problem exactly the same way. And then in part E, we're going to add one more layer of spray on top of this. Okay? And so in here, you're going to have 5 resistances. Okay? Okay. So this is Ti, T infinity. Okay. So this is our metal. This is our spray. This is our insulation. We have another R spray here. Okay, so we're going to be spraying another thing on the outside of that. So we have two spray layers basically. Okay. And then we have R convection. Okay. Right, and then just like all the previous problems, you're going to solve for TS, which is going to be right in between those. Okay. And so for parts D and E and C, I just drew the circuit, but you would kind of solve for it in the same way. So first you would find the total heat transfer throughout this entire circuit. So you take the difference in end temperatures and divide it by the total resistance. And then you set that equal to another expression for the heat transfer that has TS in there. Okay. All right. So does this kind of help with that problem a bit?
Yes, it does.
Great. Okay. Yeah. So give that one a try. You know, the homework's due at midnight. If you've already submitted, you can submit it again. And so, you know, I only look at just the latest submission for the homeworks. Okay. Okay. All right. So then now that that's done, let's get back to fins. Okay. And so, you know, just because it's been a week, you know, just to kind of remind you, fins are basically just any kind of extended surface that comes off of an engineering device. Okay. And the point of these extended surfaces is to basically enhance heat transfer to a surrounding fluid. Okay. Okay. And so visually, it looks something like this usually. Okay. Okay. So it looks like just a rod that's kind of jutting out from a surface. And then on this rod, you know, we're going to be blowing some fluid on top. That looks just like that. Okay. Okay. And so where we ended last time was we computed the temperature distribution in the fin. Okay. And so we ended up looking at a graph that looks like this. Right. And so on the x-axis here, we have x. So x is just simply the distance down the fin. Okay. And on the y-axis here, we have our parameter theta. Okay. And remember, we define theta to be what's called the excess temperature. Right. And so what all that basically means is that the theta is going to be the amount of temperature that's above the fluid. Okay. All right. So basically, it's the amount hot, or how much hotter the fluid or the fin is compared to the fluid. Okay. Right. And so what we saw was that the temperature distribution looked like this. So it started out high on the base of the fin, right? And then as you went along the fin, you know, the temperature kind of decays down just like that. Okay. And remember what we said is that at the base of the fin, which is where it's the hottest, you know, that's where we have the biggest temperature difference and hence the biggest amount of heat transfer, right? And then as the fin loses heat, you know, as it loses heat to the fluid, as you go to the end, then the temperature decreases. And then so by the end of the fin, you know, you have less and less heat transfer. Okay. Okay. And so the solution that we spent, you know, basically half the lecture deriving last time was for a specific condition at the tip of the fin. Okay. And I think last time I mentioned that there are 4 different tip conditions that we can use. Okay. And so the first one that we looked at was kind of the most general one, which is, you know, we assume that we have convection heat transfer at the end of the fin. Okay. Okay. And so today what I wanted to do is I wanted to start with the 3 other conditions and kind of just talk briefly about them. But I'm going to focus on the 4th one because mathematically the 4th one is kind of the easiest one to work with. Okay. Okay. So are there any questions on any of this? Okay. All right, so let's go over the other tip conditions. A lot of these tip conditions kind of represent roughly the same thing, but they end up working out pretty differently mathematically. Okay. And so I should actually call this number 2 because this is the second tip condition. Okay. And so the second tip condition that we can use is we assume that there's very little heat loss at the end of the fin. Okay. Okay. Right. So in other words, basically, we assume that the tip of the fin is adiabatic, okay, or perfectly insulated. Right. Which might seem weird at first because the whole point of a fin is to enhance heat transfer. And so how can we propose, or how can we specify a condition where the end of the fin is there's no heat transfer there? Okay. And so the motivation from this comes from the fact that we know that as the temperature decreases in the fin, by the time that you get to the end of the fin, you're going to have very little heat transfer there anyway, because the tip of the fin, its temperature usually reaches very close to what the fluid temperature is. Okay. And if under the case where the tip basically reaches the same temperature as the fluid, then you have no heat transfer there at all. Okay. And so that's kind of where the motivation for this condition comes from. Okay? And so mathematically, the way that you can express that, okay, is you have Fourier's law, which is the derivative of temperature. And if you apply this at x is equal to L, where L was the length of the fin, then you just set that equal to 0. Okay. Okay. Right. And so the third tip condition that we can specify is just say, maybe we know exactly what the temperature is at the end of the fin. Okay. Okay. And so let's say that, we have a temperature probe, or we have a thermometer at the end of the fin. And from there, we can just measure just whatever the temperature is. Okay? And so mathematically, it would look like this, right? So we say that theta, remember, which is basically our temperature distribution, when we evaluate it at x is equal to L, then we get, theta L, which is our, whatever we measure. Okay? Okay. Right. So that's another tip condition. Right? And so the last one that we'll go over, and this is the one that you'll probably use for most of your calculations, just because it's pretty simple, is that we assume that the fin is very long. Okay. Right. And so what this basically does is that if the fin is really, really long, then what we can basically say is that at the very tip of the fin, there's no difference in temperature between the fluid and the fin. Okay.
Is that similar to the second condition?
It is very similar to the second condition. Yeah. But mathematically, it kind of works out differently for 4. So 4 actually ends up being much simpler mathematically. So that's the one that we end up using. But physically, it basically means the same thing as condition 2. Yeah. Mm-hmm. And so the way that we prescribe this is that we can say as L goes to infinity, right, then theta at L is going to be equal to 0. Okay. Right. And so basically this says that, as we get further and further away from the base, there's going to be no difference of temperature, between the base or between the fin and the fluid. Okay. And so this condition here is actually really nice because if you remember, when we were solving the differential equation on last Wednesday, we saw that our general solution looked like this. Okay. Right. And so we had a C1 e to the mx plus C2 e to the minus mx. Okay. And so, if we have this condition here where, we're saying that as L goes to infinity, theta of L has to approach a 0, okay? Then what that tells us is that this first term, which is a positive exponential, right? So we have e to some positive number. This can exist, right? Because if that term existed, right? And so we say theta of 0 or theta of infinity is equal to C1 times e to the infinity, right? E to the infinity is just going to be infinity, right? And so there's no way for this term to exist. So just by this boundary condition, we can say that C1 is going to be equal to 0, okay? Right? And so our solution actually ends up being very simple because our C2, right? Our C2 ends up being theta B, right? Because if you remember, our other boundary condition that we always apply is that, when x is equal to 0, then the temperature difference is just going to be whatever the temperature difference is at the base. Okay, so that's going to be theta B, right? And so from that, then we get our kind of the simplest expression for this, which is theta of x is equal to theta B e to the minus mx. Okay. And so for a lot of the problems that we'll do with fins, this is the condition that we'll usually assume because it's mathematically it's kind of the simplest one. Okay. All right. Any questions on any of this? Okay. All right. And so before we jump into an example, there's one more thing that I want to show you guys how to compute, which is how to compute the total amount of heat transfer from the fin. Okay. Because as engineers, that we're going to be designing these thermal systems, and if we're going to make the decision to add a fin, then we want to know naturally how much heat that we can expect to be to be lost through to the fin. Okay. And so computing this is actually pretty simple because what we can say is that if we have a fin like this, okay, right, and we basically want to compute all the heat that's lost to the fin that's out here, okay. Right. And so if we want to compute all that heat transfer, what we can basically observe is that in order for the heat or just any thermal energy to reach kind of the outer surface of the fin, it has to pass through the base at some point, right? Okay. Because there's no way, for the fin to lose energy, because the fin is a passive structure. So the fin we know isn't producing any heat, right? So we know thermal generation is 0 within the fin. And so any heat that actually exits from the fin, it has to pass through the base at some point. Okay. And so to compute the total amount of heat transfer from the fin, all we have to do is compute the conduction heat transfer at the base. Okay. Okay. And so basically, we're going to compute this. Okay. And so we can say that QF, where QF is going to be the heat transfer from the fin, is going to be equal to minus K AC d theta dx. Okay. Where we're basically just applying Fourier's law here. Okay, so we have the thermal conductivity of the fin, we have the cross-sectional area, and then we have the derivative of the temperature distribution. Okay. And then this is going to be evaluated at x is equal to 0, which is the base of the fin. Okay. And so if we actually apply that to our previous solution here, right, which is our simple kind of theta, theta of x here. Okay. And so if we say that theta of x is equal to theta b e to the minus mx. Okay. And so if we take the derivative of this and plug it into this formula, we can say that qf is equal to minus k AC times minus m theta b e to the minus mx. Okay. And so all I did for this was I plugged in this formula here into here. So I took its derivative. And so by taking the derivative, we get a minus m out in front. Okay. And if you kind of remember the fact that m here was a combination of all the thermal properties of the of our fin, right? So m was equal to HP over KAC. Okay. Right. Where H is our convection coefficient, P was our perimeter around the fin, K was our thermal conductivity, and AC is the cross-sectional area. Okay. If we plug all that in, and we cancel out a bunch of these terms. Okay. And so these negatives are going to cancel. We're going to evaluate this at x is equal to 0. So this ends up being 1. Okay. Then what we get for the QF for condition 4 is going to be equal to this. Okay. So we're going to have square root of HP KAC times theta B. Right. And so that formula down there is basically the total amount of heat transfer from a fin if we assume the fourth tip condition. Okay. All right. Any questions on this before we do another example with the fin? Okay. All right. So let's do an example just to kind of pull all this together. Okay. And so let's say that we have a very long fin with a diameter of 5 millimeters.
Professor, can you go back one page in your notes really quick?
Sure. Mm-hmm. Right. Are you good?
Yes.
Okay.
Good.
Okay. And so in this example, let's say that we have a very long fin with a diameter of 5 millimeters. Okay. And so the key word so far here is very long, right? And so if the problem basically says that the fin is very long, then we can apply condition 4. Okay, so which is great because that's kind of our simplest condition right there. Okay. Another thing we know is that the base of the fin is maintained at 100 degrees Celsius. Okay, and so basically this tells us that TB, which is the temperature at the base, is going to be 100 degrees C. Right? Okay, so let's draw a diagram of this. Okay. So let's draw a very, very long fin. Okay. And so we know that TB here is going to be 100 degrees C. Okay. This fin is going to be cooled by air. Okay. And so this air has a temperature of 25 degrees C. And the convection coefficient here is going to be 100 watts per meter squared K. Okay. All right. And so we're going to assume that the rod here or the fin is made of aluminum. And so the thermal conductivity for that is going to be 180 watts per meter K. Watts per meter Kelvin. Okay. And so we want to solve for two things. So first of all, we want to, or I guess three things. And so we want to solve for the temperature distribution in the rod. Okay. We also want to solve for, what's the total heat transfer rate? Or in other words, the total amount of heat lost from the fin. Okay. Right. And then 3, after we actually solve those, we'll be able to actually solve for how long the fin is. Okay. All right. And so let's start with number 1. Okay. And so remember, when I'm asking for temperature distribution, I'm asking you to solve for either T of X or theta of X. Okay. And so since this is a fin, we're going to solve for theta of X. Okay. Okay. And so since, this is a very long fin, we can basically assume that our solution looks like this. Okay. So our solution here is going to be theta B e to the minus mx. Okay. And so from here, there are 2 things that we have to specify. So we have to specify theta B, and we have to specify m. Okay. So theta B is simple. And so remember, theta B is just the temperature difference at the base of the fin, right? And so since we know that the base is maintained at 100 degrees C, okay, theta B is just going to be 100 minus the fluid temperature, which is 25. And so theta B here is going to be 75. Okay? And then m, we're just going to plug in all the parameters for m right here. Okay, so m is HP over KAC. Okay. Right. And so we have all these parameters from the problem. And so, of course, you'd have to compute the perimeter and the cross-sectional area from the radius. Okay. But if you plug all that in, you should get an m of 21.08. Okay. And so we put all those together, and then we can get our solution for the temperature distribution. So we have theta x is equal to 75 e to minus 21.08 x. Okay. Right. Any questions on that? Okay. All right. And so the next part is we want to solve for the total heat transfer rate. Okay. So in other words, we want to solve.
Sorry, could you go back just for 1 second?
Oh yeah, sure. Mm-hmm.
Okay, thank you. That was it.
Okay. And so when we want to solve for the total heat transfer rate, what we're solving for here is QF. Okay. Right. And so QF, remember, is going to be minus K AC d theta dx. Okay. So that's the formula in general. But since we have the case of a very long fin, what we can do is we can plug into the formula that we derived on, the page 2 pages prior. Okay. And so this is simply going to be H times P times KAC times theta B. Okay. And so we can just simply plug in numbers for all of those guys. And what we get is 5.6 watts. Okay. Okay. Right, so that was part 2. And so part 3 of this problem, we want to find out, how long is this fin actually? Okay. Which might seem, difficult to solve because, we weren't, that's a physical dimension that we weren't given in the problem. But what we do know is that, we're assuming that the temperature distribution or the temperature of the fin very far away is going to be very close to the fluid temperature. And so one way that we can, approach this is we can say that, as we go farther away from the fin, theta is going to be is going to approach 0. Okay. And so mathematically, it's going to be impossible to get perfect 0 from this equation, but we can kind of get close. Okay. And so what we can basically say is that at x is equal to L, okay, at x is equal to L, the temperature difference between the fin and the fluid will be only 1% of the original temperature difference. Okay. And remember, the highest temperature difference that you'll have in a fin is at the base. Okay. And so if we say that at x is equal to L, theta is going to be 1% of that, we can basically say that theta of L is equal to 0.01 theta B is equal to theta B e to the minus m times L. Okay. And then from here, what we can do is we can solve this equation for L. Okay. And so solving for L, basically we're going to cancel out theta B on both sides. Okay. We're going to take the natural logarithm of both sides. Okay. And so we have natural log of 0.01 is equal to natural log of e to the minus mx, or e to the minus ml, sorry. Okay. And since we're taking the natural log of an exponent, these guys are basically going to cancel out. And we have ln of 0.01 is equal to minus ml. Okay. Right. And then from here, we can just say that L is equal to ln of 0.01 divided by minus m. Okay. And we plug in our value of m. Remember, our m was 21.08, and we get that L is equal to 0.22 meters or 22 centimeters. Okay. And so basically what we're saying is that the fin has to be at least 22 centimeters long in order for us to apply our, our assumption here. Okay. Any questions on these two parts of the example here?
I guess a question more about the concept. So
Sure.
finding this measurement for the length of this fin. So couldn't you also say that at this length, anything longer, it's pointless to have the fin be that long?
Yeah. Yeah, no, that's a great way to interpret that too. So, and that's another reason you would do a calculation like this. So if you're designing a fin for, some kind of device, usually you don't want the fin to be too long because you don't have, a ton of space. Like you can imagine, riding a motorcycle and, having two fins jutting out into the opposite lanes and, saying to the soccer mom, like, sorry, it's for heat transfer, that usually doesn't fly. And so, another thing that you're usually interested in thermal design is, what's the length of the fin that I need to get basically maximum amount of performance from this fin? Yeah. Mm-hmm. Right. Any other questions on this? Okay. Okay. So that's that basically covers how do we solve for a temperature distribution and the heat transfer within a fin. Now let's talk about how we actually evaluate fin performance. Because not all fins are the same, right? And so, we have to have a way of basically evaluating how effective a fin is. Okay, and so to do that, we have this metric here called effectiveness. Okay. Okay, and so the symbol for that is basically epsilon sub f. Okay. And the formula for that is the following. And so effectiveness is going to be computed as QF, where QF is the total amount of heat transfer from the fin, right, divided by HAC theta B. Okay? And the reason, and kind of the origins of this equation here is this is a ratio of how much heat transfer is coming out of the fin compared to the amount of heat transfer that we would get if no fin was there. Okay. And so we're basically, comparing these two situations. Okay. And so in one situation, you have a fin. Okay. And then from this fin, you have QF. Okay. Right. And so QF is the, total amount of heat transfer from the fin. Okay. Which is, we just learned how to compute. Versus, say that we didn't have the fin and we just had kind of a flat surface. Right. So if we take this same kind of cross-sectional area, AC, okay, then if, without the fin here, this heat transfer is basically going to be Q is equal to H times AC times theta B. Okay. And so this is basically heat transfer. Heat transfer on that same plot of material if we didn't have the fin. Okay. And so basically you can think of effectiveness as basically how much this fin is enhancing heat transfer. Okay. Right. And so generally, practically speaking, the amount of effectiveness that you get, it really depends on what kind of industry that you're working with. But generally what you would want is you would want your effectiveness to be greater than or equal to 2 for a good fit. Okay. And so basically what that's saying is if you're going to go through the trouble of putting a fin on your structure, it should be designed such that you enhance heat transfer by a factor of 2. Okay. And if you're not kind of reaching that threshold, then it kind of brings up questions of why are you even building this fin anyway if it's not going to be that effective. Okay. Right. Any questions on this?
Just generally, where are fins typically like applied, like missiles and stuff?
Yeah, so it's I mean the one that I'm probably most familiar with is in electronics. And so in electronics, basically you have basically the processors and any kind of graphics cards, those things are producing a lot of heat. And so to kind of account for that, or to kind of offload that heat and kind of prevent the computer from melting itself, the designers for these systems, they put fins on these guys, to basically help increase the surface area. And so that when you blow air over it, then it's going to help, cool your system. And so those are the ones that, like, visually, I know what they look like, and I've seen them a lot. But fins are basically used anywhere where you, most commonly, they're used to offload some heat. And so if you have a part that's overheating, just from its its regular use, then you can add a fin there to basically help cool it down. Yeah, so car radiator is another, big example of that as well. Mm-hmm.
Another one would be like a fridge or refrigerator.
Mm-hmm. Yep, another great example there. Yeah, anytime you want to basically enhance heat transfer to some, most of the time it's air, but sometimes it can be water too. If you're designing something for like a submarine or a boat, anytime you want to enhance heat transfer to a moving fluid, you're going to construct a fin.
I have a question.
Yep. Mm-hmm.
Would we lump in, because like radiator is more of like a coil like line system, with like a bunch of different passes. I mean, is that lumped in as the same thing here as a fin, or is that treated a little differently?
Yeah, so I mean, a lot of the same. I mean, the idea of the radiator is the same, is to basically, enhance heat transfer. I mean, for the class, just for kind of simplicity, we're kind of just sticking to fins that just look like a rod that goes in one direction. But basically, anything that you're constructing to enhance the surface area, all of those can be considered fins. Yeah. Right. So, question. So, what's a good range for efficiency? Yeah, it's a good question. So, usually for this, so this is effectiveness. We'll go over efficiency a bit later. So, effectiveness, usually you want to be at least greater than 2, but the exact numbers and the exact thresholds are going to depend on your industry, right? Because a factor of 2 might be good for like electronics, but for like a car or automotive, 2 might not be good enough, because sometimes you'd want to have bigger enhancements. So it really depends on on kind of the field that you're considering. Yeah. Mhm. Okay. And so let's actually compute this for our really long fin. And so we actually plug in the expressions for all those, and this is basically the same configuration that we did in our last example. We get the following expression, and so we get epsilon of f is equal to kp over HAC. Okay. All right. And so if you compute this, like you basically take your thermal conductivity and you divide it by H times perimeter divided by AC, which is your cross-sectional area, that's how effective your fin is going to be. Okay. So this is really nice, actually. So, all of these parameters here in this formula are very easily obtainable, right? So a lot of times you know what material you're using, the geometry, so you can get P and AC. And if it's a fairly constrained system, then you'll probably know what H is too. Okay, so before you even construct the fin, before you even do anything, you can just plug into this formula here and compute its effectiveness. Okay. And so, this formula is nice, but I do want to highlight kind of some things about this formula here, because even though this is, it looks like a fairly simple formula, there's a lot of information that we can actually derive from this that can actually apply to more complicated fins like a car radiator as well. Okay. Okay. And so what I'm basically going to do is I'm going to look at basically each of the parameters here and basically make some observations on how that affects the effectiveness. Okay. All right. So let's start with K. As remember, K is our thermal conductivity. Okay. And since K is in the numerator of this expression here, what this basically tells us is that if we increase the thermal conductivity of the fin, then it's going to increase the effectiveness. Okay. And so it's basically advantageous for you if you want to make your fin as effective as possible to use a material that has a high thermal conductivity, right? And so a lot of times you're going to see fins constructed of metals, right? Because if you remember from the beginning of class, metals tend to have much higher thermal conductivity than many other materials, right? And so you don't really want to make a fin out of plastic, because that's plastic. Plastic is normally pretty insulating, because then that's not going to make for a very effective fin. Okay. And so, no matter what kind of geometry that your fin is, whether it's, a coil, whether it's just a rod, generally you're going to want to use metals for your fins, because that's going to be what's most effective. Okay. Okay. Now let's look at these two guys together, actually. Okay. And so the reason I kind of group those P over AC together is that this is the ratio between the perimeter and the cross-sectional area. Okay. And so basically, if we increase this ratio, okay, if we increase this ratio, then our effectiveness will increase.
quick question about the perimeter.
Yeah.
That's like the perimeter of a cross section, right?
Right. Yes. Yeah. So it's you know, like for a, you know, like in the example we did was a cylindrical fin, and so we're talking just the perimeter around kind of the circle. You know, if you took a cross section there.
Okay.
Yeah. All right. And so, you know, you know, this factor here in green, this kind of tells us about, you know, what kinds of shapes actually make good fins, right? And so, you know, if you have a certain amount of material, you know, there's lots of different shapes that you can use for that, right? But certain shapes have a higher perimeter to cross-sectional area ratio, okay? And so in general, what makes a good fin shape are shapes that are relatively thin, okay? Okay. And so the reason for that is you have something that's thin, you know, you're going to have a lot of perimeter compared to cross-sectional area there. Okay. So actually in the homework, you know, I'm actually going to ask you guys to design a better fin. Okay. And so I'm going to have you do basically almost the same thing as the, you know, the example that we just did. And so I'm going to give you a fin that starts out as a cylinder. Okay. And then what I want you guys to do is basically to improve it by changing its shape. Okay. So a cylinder, you know, is actually one of the worst shapes for a fin because a cylinder has a very high cross-sectional area compared to its perimeter. Okay, and so a lot of times you won't see fins in the shape of a cylinder just because it's, you know, not that good of a shape. If you do see things in the cylinder, you might see it in the form of like a coil. Okay, because a coil is something where you can take a cylinder and you can kind of twist it around and increase its surface area quite a bit for kind of a small amount of space. So that's probably the only application where you would see a cylinder, but you would never see a fin that's just a straight cylinder that goes out just like that. Okay. Okay. And so the last one I want to highlight here is H. Okay. And so H here is in the denominator. Okay. And so what this basically tells us is if we increase H, this decreases the effectiveness of our fin. Which might be really confusing at first, right? Because remember what H represents. So H represents how easily heat can move from the fin or from any solid to a fluid, okay? And so and so what this basically tells us is if we increase the amount of heat transfer to the fluid, this actually makes our fin less effective. And so it's really kind of counterintuitive if you kind of think about it. But if you think about it like this, right? So remember the fin, or this fin effectiveness right here, this epsilon F, represents the ratio of, you know, of heat transfer if the fin was there versus if the fin was not there, okay? And so H, you know, H is just a property of the fluid. So it's actually not a property of the fin itself, okay? And so if you have a situation where your H is already really high, right? And so say if you're cooling something with water instead of air, then adding a fin to something where, you know, the fluid is already really good, you don't really gain that much benefit, okay? Okay. Right. And so if we go back to kind of the situation back here, right? And so if we look on the right, say that we had, you know, a fluid here with a really high H, okay? And so if the H is already really high, from this little patch right here, you know, we can already expel a lot of heat just because, you know, the H is already really high, okay? And so when H is already really high, you know, there's really no point in adding a fin because we're not really going to get that much benefit from it, okay? And so that's why you kind of have this inverse relationship for H down there, okay? And so, you know, when you first look at it, it might seem kind of counterintuitive. And so it's not that increasing H makes our fin worse. It just makes it so that, you know, adding the fin, you know, we're kind of getting diminishing returns. You can kind of think of it like that, okay? But of course, increasing age is always going to increase the total amount of heat transfer because that, enhances the fluid itself. But, the benefit that you get from adding a fin just becomes less when your age is higher. Okay. All right. Any questions on any of this? Okay. All right. So that's effectiveness. So that's one way to rate a fin's performance. And so another metric that we can talk about is the fin's efficiency. All right. And so the formula for efficiency actually looks very similar to effectiveness. Okay. And so the formula for efficiency is the following. Okay. All right. So the symbol that we give efficiency is this symbol eta right here. Okay. Right. And so the formula for this is given by the following. And so on the numerator, just like before, we're going to have QF, which is our total heat transfer from the fin. And on the bottom, we're going to have something that looks very similar, but not quite. Okay. And so we're going to have H times AF times theta B. Okay. And so the only difference between fin effectiveness and fin efficiency is this area right here. Okay. And so this area right here is the total surface area of the entire fin. Okay. Right. And so basically what this is, it's another ratio, right? But this thing on the bottom right here is, this is kind of the theoretical maximum heat transfer that you can get from the fin. Because kind of the best case scenario for your fin, or the conditions where you achieve maximum heat transfer, is if the entire fin was the same temperature, right? And so if the entire fin was the same temperature as the base, okay, and so you have basically theta B throughout the entire fin, then that's going to result in a, that's basically as efficient as you can get for the fin, okay? And so what you're computing here is another ratio, which is, the actual amount of heat transfer that you get from the fin, which is QF, divided by kind of the theoretical max, okay? And so efficiency here is always going to be a number between 0 and 1, okay? Okay. Where 1 being the theoretical max, which is, impossible to achieve. And so, depending on what this number is, will basically tell you how efficient your fin is at transferring heat. And so, again, this is something where, it depends on kind of the industry that you're working with, on what's a good efficiency. But, maybe a good rule of thumb for this one probably be around like, 0.5 to 0.7, I think would be, those are pretty efficient fins, at least from my experience. Yeah. Okay. All right. Any questions on this before we move on to 2D conduction? Okay. All right, so that's everything about fins, okay? And so the next thing that we're going to talk about here is more general 2D conduction. Okay? And so fins kind of presents a kind of a specialized case of 2D conduction, and that's kind of the reason I talk about them together, where if you remember from fin, we had a heat transfer through conduction in one direction, right? But then perpendicular to that, you have heat transfer through convection off the sides of the fin. Okay. And so this is technically 2D conduction here because, we have heat transfer that's going in different directions, kind of constrained within a 2D plane, but it's a very specialized case. But there are also other situations in general where you have heat transfer that's going in 2 dimensions. Okay, and so in order to solve for this, and we can generalize this to 3D. The way that we actually solve for this is to solve the 3D heat equation. Okay, and so the generalized heat equation looks like this. Right, so we have our second derivative with respect to x, and so just like in the 1D case, but now it's a partial derivative because now we have both, we have all three x, y, and z. Okay, and I'll put the time term here, even though we're not going to do anything with it yet, but next week we will. Okay. Right, so this is the full kind of this is the full heat equation here. So no assumptions on this guy at all. Okay, and so this equation here is very much a partial differential equation, right? And with kind of the limitations of this class, for all intents and purposes, this is going to be impossible to solve. Okay? So to actually solve this equation, you would actually need to take like an extra class in partial differential equations. And so I think the class that we have for that here, I think is 431. I'm not sure, but Dr. Weiss teaches that class. So that basically is a class on how to solve equations like this. Okay, but we're not going to do that because as you can imagine, it takes an entire semester for Dr. Weiss to teach you how to solve PDEs. There's no way we're going to do it in 10 minutes at the end of this lecture. Okay, and so we're not actually going to be solving this equation. But what we can do is we can kind of do a simplified version of this, or basically an approximation for certain specific shapes. Okay. And so the key word here is specific shapes, okay? And so the reason I kind of highlight that is, everyone knows that 2D and 3D heat conduction is pretty complex. But kind of throughout the history of the entire, world of humankind, there are certain shapes that tend to show up more often, right? And so, these are shapes that are seen commonly in, a lot of devices that humans make, okay? And so what people have done is that people have done a lot of experiments on these specific situations and specific shapes, and they've kind of put their results into some tabulated tables or tabulated data that people can access so that they can kind of analyze these systems without having to go through this entire kind of complicated equation. Okay. And so, the way that we're going to do 2D conduction is that we're going to look at, specific situations or specific shapes, and then use something what's called a shape factor in order to compute its, its heat transfer. Right? And what you'll see from the shape factors is that they're actually very similar, or the way that you use them is extremely similar to how we use our thermal circuits. Okay. And so, if you understand thermal circuits, then, shape factors will just kind of be just another step up from that. All right, any questions on any of this? Okay. All right, so the formula here we have for shape factors is the following. Okay? And so if we want to basically solve for the heat transfer, okay, and so this is heat transfer in 2D situations or 3D, okay? this is going to be equal to something called S, where S here is our shape factor, multiplied by K, where K here is our thermal conductivity, multiplied by delta T, okay? So let me label this, okay? Okay, so this S here is our shape factor, and I'll define that more in a second. Okay? K here is our thermal conductivity. Okay. And then delta T here, this is just the temperature difference. Okay. Right. And so this S, you know, this is kind of the new guy here, right? And so shape factors, you can almost think of these as like, you know, coefficients that quantify the heat transfer from certain geometries. Okay. Okay. And so where you would look it up is that you can look these up in a table. Okay. And specifically for in the textbook, this table is going to be table 4.1. Okay. And I'll show you what that looks like, you know, after this. Okay. But there's, you know, one thing I want to point out before we do that. Okay. Okay. Because if you look at this equation that we have up top here, this Q is equal to SK times delta T. This should look, you know, very similar to you guys, right? Especially, you know, compared to, you know, one of the homework problems that we went over at the beginning, right? Let me do this. So let me define a resistance, okay? And let me define this resistance to be 1 over SK. Okay? And I'll call this R2D. Okay? Okay? And so if we do that, then our formula becomes Q is equal to delta T divided by R2D. Right? And so this formula, you know, when I put it in this form, basically looks exactly like, you know, our thermal resistance formulas that we've been using all the way up until this time, right? And so you can kind of almost think of like, you know, the shape factor as like a thermal resistance that occurs due to geometry. Okay. Okay. Right. And so when we do an example, probably we'll do the example next week because we're just about out of time. You'll see that, you know, you can use this shape factor basically exactly like, you know, a thermal resistance that we've done before. Okay. It's just that, you know, and they kind of encapsulate or they kind of illustrate the fact that in 2D and 3D, you have additional, you know, resistance to heat transfer just purely based on, you know, the shape of your object. Okay. All right. Any questions on this before I show you some examples of some shape factors? Okay. All right. So I'm going to show you basically a picture from the lecture notes. And so, you know, everyone, you know, these lecture notes are available to everyone. But I will say that the textbook has a much more comprehensive table than this. Okay. Right. So this is page 15 in lecture notes 03. Okay. And you can see here that these are some examples of some shape factors. Okay. And so basically the way to read this table is that on the leftmost column here is you know, just kind of a text description of what's going on. Okay. And so if we look at this first line here, so this first entry is an isothermal sphere buried in a semi-infinite medium. Okay, and so basically what that means is that you have a sphere here that's buried underneath the ground, right? And so what you have in the problem here is that the sphere is a certain temperature T1, and the top of the of whatever medium, or like the soil or something, is T2. Okay. In the third column here, you have some restrictions, and so you have to you can only apply this shape factor when these conditions are met. And so the conditions are that Z, which is the amount that this sphere is buried, has to be greater than d over 2, where d is the diameter. Okay. And if all these conditions are satisfied, then the formula for the shape factor is given by the following here. Okay. And so the shape factor S is going to be 2 pi d over 1 minus d over 4z. Okay. Right. And so that's kind of just one example of the different of a shape factor, and you can read kind of the other shape factors here as well. Okay. But on next Monday when we pick this up, what I want you guys to remember is that shape factors, you can kind of almost think of them as like a resistance that's based purely on geometry. Okay, because the big difference between 1D and 2D is that geometry kind of plays a much bigger role in how heat kind of flows through an object. Okay, and the way that we can kind of summarize those in just one simple number is the shape factor. Okay. All right. Any final questions on this before we wrap up for the week?
Do those shape factor formulas come from solving the partial differential?
Yeah, so part of it is that, but a lot of them actually came from experiments too. And so what I think the way that these shape factors developed was, someone first ran an experiment on something similar to this, and then they were able to tabulate the results. And then later on, people solved the heat equation and then kind of verified these expressions. So a lot of these expressions are relatively clean. This one looks kind of messy, and kind of the reason they look clean is because they went back and verified it with the heat equation. Yeah. All right. Okay, so if there's no more questions, that's all we got time for this week. So thank you guys for tuning in for this short week. And so once again, I hope you guys have a good weekend. Remember, homework's due tonight, and so if you have any more questions on that, I'll be available for the rest of today, except between 5:30 and 7, because that's when I'm giving another lecture. But definitely reach out if you have any questions on that. So thank you guys for tuning in. Have a good weekend, and I'll see you guys on Monday.
Thanks, Professor. Have a good one.
Thanks, you too.
Thank you.
I actually had a question about one of the homework problems.
Sure. What's up?
It was actually the first problem on there,
Okay.
asking how adding extra layers could actually reduce the thermal conductivity, or it could increase resistance.
Yeah. Mm-hmm.
No, sorry, it could reduce resistance. So I was a little confused about that. I kind of answered that if they're set up in parallel, then that would reduce the efficiency of the resistor.
Yeah, so the kind of the thing that's unique, because this homework is all based on radial systems. So we have basically cylinders and spheres, and so kind of the unique thing is that when you add insulation thickness, and so you add kind of a layer on top, you're not only increasing the thickness of your object, but you're also increasing its surface area, right? And so
right. So we had that critical thickness, right, where the surface area is too big for the volume.
Exactly, right.
Okay,
so,
that's coming back to me now.
Yeah. So if you kind of look up that part in the notes about critical thickness. So basically what's happening is that as you increase the surface area, you're giving more space for convection to kind of act on your system too. And there are some situations where, you actually reduce the resistance, even though you're adding insulation, you're increasing the conduction resistance, but you're also reducing the convection resistance because you're basically increasing the surface area of your object.
Okay, yeah, I missed that in my notes, but that's it's all coming back to me.
Cool.
Well, thanks.
Yep.
Enjoy the rest of your weekend.
Thanks, you too. Ahmed, did you have any more questions? Okay. So if not, I'm going to go ahead and close the call. So have a good weekend. I'll see you on Monday.